This is Anna Doblas from University of Massachusetts Dartmouth. I would like to show you one of our latest tools to reconstruct holographic images using non-telecentric systems. This work has been led by my former PhD student Brian, and it was presented in an Optical conference this past August. And I need to say that this research has been a close collaboration within Dr. Trujillo at the EFA University in Colombia. So the whole idea about digital holographic microscopy is that we can get quantitative phase images. So quantitative phase images it's a required modality for those samples that they they are transparent, so they present low absorption when they are illuminated, and you don't need to stain it, so it's label free, so you don't have any toxicity added, and it's really important to do drug studies. So the whole idea, because you are recording the complex distribution, you can reconstruct both the amplitude and the phase imaging, and the key part is that you do it with a single image, so it's really fast, and you are able to track the behavior of the cells within the time. So the whole idea it's a hybrid imaging method. So a hybrid imaging method means that you have your optical hardware, your optical system, but you also need a computational framework. So the optical system is just like the traditional Mach sender interferometer, so your sensor records the interference pattern between an object and a reference, and within the object arm you introduce a microscope. So you're gonna have the light scattered by the specimen is gonna get imaged by a conventional microscope, and it's gonna, like the tube length kind of gonna depend on the distance to the tube length. So you might be working on telecentric or non telecentric regime. I'm gonna show you what is the difference in a couple of slides. But regarding with the, and here is where you record. So you record the sensor, record the hologram. So the hologram, it's the summation of the intensity information of the object and the reference, and then you're gonna have the real and the virtual images. So it's just the multiplication of the complex distribution of the object and the reference conjugating one with respect to the other. So the difference between telecentric and non-telecentric is we have assumed that the sample is illuminated with a plane wave. So telecentric agent system is called a focal because you have a plane wave in both sides on the object and the image spaces. So for that to happen, what that means is that the pupil plane is placed at the front focal plane of the tube lens. So you're gonna have a plane illumination, and telecentric agent system, it's really important because you're gonna show that the value of the retrieved information always gonna be the same regardless the position of the sample, but it's also important because you don't have the lateral magnification, it's always the same regardless the position of the object because you have a plane wave in the image space. However, a lot of time is people has not adopted the telecentric setup, so some DHM systems are working or operate on a non-telecentric configuration. So what that means is that in the image space you have a spherical wavefront, and you have this spherical wavefront, it's overlap to the phase information of your object. So that means that you need to retrieve it, you need to kind of compensate it computationally. But because the spherical wavefront multiplies the image of your object, makes by default that the system is not linear invariant. So what is that problem? That problem is where I'm just pointing out here, where you have your sample, and immediately your sample is gonna be within a plane wave, but the other one, your same sample information, it's overlap with the spherical wavefront introduced by the non-telecentric configuration. So you really need to compensate it computationally and excuse me, making small differences you make that you have this kind of curve reconstructed face image, so not be able to have exactly the same value of the face independently of the position. And we show, or during my PhD work, we show that this is extremely important, not when the sample is in the middle of the field of view, but in particular for the samples that they are kind of like at the edges of the field of view. Like you can see that here we were making an error about 2 pixels from the center, and then like a less than 5% error on the curvature of the spherical waveform. And we can see that when the phase dip is at the edge, definitely the error is so many higher. So non-telecentric, you need to compensate for the spherical waveform, but that compensation needs to be extremely accurate if you are using the phase values for diagnosis or for comparing or categorizing samples, because your value might be distorted, not because the sample itself, but more about your reconstruction method. So this is extremely important when right now we always want to use systems that they are already at size, so we want to minimize the effort. So when you try to put a system, a DHM module within a commercial microscope, a lot of time the commercial microscopes are focused for intensity-based imaging. So you don't care about the phase. A lot of time they work in a non-telecentric configuration, right? So it's really important to kind of have some nice framework where we can get quantitative phase imaging, so we are able to compensate for the spherical waveform introduced by the optical configuration in a fast and in the best way that we can. So this is kind of like where we are. So you have your hologram and you do the Fourier transform, and because you have the tilted reference wave and then you have the spherical waveform, it's important that you need to kind of like the tilted reference wave is related with the angle with the object and the reference, and then the spherical aberration is given by the curvature of the spherical waveform introduced by the non-telecentric configuration. So the accurate, the true phase map needs to be the one that you retrieve through the method, but you need to subtract both contribution, the angle of the interference angle and the spherical waveform from the optical configuration. So I'm going to talk to you about how we are doing it. So the digital reference, it's easy. We just need to do the angles, and for the angle we just need the center of the plus one term, so the P and Q. Y for the Q, and that's how we can compensate for the angle. And when we are doing the centering here, this is our plugin. We can just kind of select where is the crop, and then you're gonna say where is kind of like the middle right here, and then that's how we're gonna compensate. When it's compensating, this is the map when it's already compensated by the linear tilt, and you just see the spherical waveform. So for the spherical waveform, the method already has like a binarization, so estimate by itself the center, and it also estimate by itself the curvature. So this is kind of like how it can estimate the center and the curvature to kind of provide the compensative one. So the whole idea is that we use the one that is not compensated, we use Otsu method for binarizing. So we create this kind of concentrics, and we kind of get the curvature for one of the concentric rings and measure it, and then the center. And this is another example where we have the non-compensated, the compensated with the linearity, but not the spherical, and then the compensated one. And when we have the curvature, for the curvature we can say that this is gonna be our values, pixels are related with the value of M and N. So that was an outcome of the paper led by Dr. Sanchez Ortiga in 2014. So this is kind of like a demo of the open tool that we have proposed. So here you have the holograms. You can manually reconstruct the plus one term. and then you try to be pretty centered. You can play around. So the idea is that when you play around, you try the spherical waveform to be as centered as possible, and then you see what is this after compensating, and then you can you center the filter, and then you create a value of M&N. And you can do just creating the filter, but you also have a fine tuning of the value of M&N to kind of see that the background is really uniform. So this is us playing with the value of M, checking what is the best uniform one. So something that I don't know if the demo shows right now is that we have also added automatic minimization about it. Like if you don't want to play, you can definitely enable the minimization. So what it does is using the standard deviation as the minimization cost function, and there are different algorithms. It try to from the spherical, from the compensated phase map of the third. So the one that is still disturbed by the spherical waveform by itself try to estimate the values of the spherical waveform to get a phase image without compensation. It's really important sometimes to change the color map. So especially when you are changing, because you want to kind of see which one has the more uniform. So for example, Paula color map, if you bear discrimination about the uniformity of the framework. And this is kind of like the summary. We have everything on the GitHub, and we have also experimental holograms and the codes and the user interface view. Again, something that we care a lot about it is minimization of the user input. We know like a lot of time the way that we develop the algorithms is to new grad students coming for the topic, so we understand that your knowledge is not deep and enough sometimes, so we want to develop these tools that they are useful for seniors and acknowledgeable researchers, but also for those grad students that are going into the input and they are asked to reconstruct an image and they don't know how. So there are a couple of things to do. There are ways of making the algorithm. When you try to minimize things, sometimes you don't get to the best option. So a lot of time is based on the thresholding method, and we try to threshold the plus one term from the beginning, but we have seen a couple of problems depending on the signal to noise ratio of the hologram. So we would like to do that step completely automatic and kind of further reducing the reconstruction times. And at the end, the whole idea is to have a single algorithm regardless if it's telecentric or not telecentric. So that are things that we are going to work in the future. We want to acknowledge our collaborators, our funding, and every member of the research groups that have been involved in this research product. And please, if you have questions, do not hesitate to email me or contact us. Thank you.